This is hot off the press. Yesterday in Bell Labs, we had visit of the Secretary of Energy, Secretary Granholm, and we also had Senator Menendez and Congressman Malinowski, so the two representatives for the state of New Jersey, visiting us at Bell Labs. And this is just illustrating how iconic the location and the site of Bell Labs is in terms of American entrepreneurship, in terms of American innovations. Many of the technical inventions that shape our life today have happened at that site, and we are still thriving with inventing the future. And many of these inventions, like the transistors, have led to Nobel Prizes. So we're very proud of that history. And I sometimes say to my wife, when we have yet another Nobel Prize, I'm here now for 13 years. We had 3 Nobel Prizes in that period. We always have a bit of a celebration and tell my wife, can you imagine I go to work and I'm going to be seeing Nobel Prize winners? It's quite a unique place. So with a 10-year horizon out, let me talk a bit about 6G. And talking about 6G, so we're in the middle of the rollout of 5G, 6G, the industry agrees this is still 10 years out, 2030. But let me maybe start with generation 0. Cellular networks have been invented at Bell Labs. Already in 1947, there was a memo that went out, and you see something like 20 people here in CC, and that is a true carbon copy because email didn't exist in those days. That went around, and the memo described how to provide a mobile radio service across the nation to any equipped vehicle. It does that by reusing spectrum in small areas. So basically inventing cellular sectors, reusing spectrum, inventing the hexagons. 1947, it's actually the same year as the transistor, also at Bell Labs in New Jersey. But it took many more years before that then became a reality. Mind, it was to any equipped vehicle. The mobile handset was really created by this guy, Marty Cooper. Analog telephone, and admittedly he was not with Bell Labs, he was with Motorola, and he created it was in a project called Phone in a Shoe, inspired by some spy movie. People of my generation will remember Maxwell Spy, and he could pick up his phone, pull out the antenna and talk. So but it looks more like a brick that needed 10 hours charging for 30 minutes speak time. And Marty Cooper admitted that this was not practical. He just wanted to prove it can be done, a mobile handset. And the first call he made in 1973, he made it, they hooked up the antenna system to a network in New York, and he made a call to his competitor researcher at Bell Labs, basically to say, got you. So Bell Labs was beaten on the first mobile handset, but Bell Labs, played an important role in the rollout of the commercial service then that started in '84. So it took another years from the research concept to the commercial rollout. Analog handsets. And people of my generation will remember quality was not that good, but it was also horrendously expensive. It was actually a status symbol. I remember people that had it in their car, and at a crossing, people would take out their handset and show off. And if you knew how much spectrum was available, you almost knew for sure that some of them were just pretending, just to show off. It was a status symbol. You even could buy fake phones in those days. So the democratization of the cellular networks happened with the digitalization, the digital phone with GSM. In the early 90s, it was Nokia actually that realized the very first GSM call. You see here the Finnish Prime Minister. These were also the heydays of the Nokia handset and of other companies. Several companies that were also flourishing in Belgium, Siemens, Alcatel, OneTouch. Some people will remember companies that are now merged all into Nokia. And so since then, the industry has turned out approximately every decade a new generation of networks. And with every generation, there were new radio technologies using higher frequency spectrum and wider bandwidth to enhance the capacity. Every generation also saw new compute platforms that enabled new applications, and you see the iconic representation here, and new network platforms. We moved from the analog to the digital with GSM. People of my generation will remember the ISDN days. Right? And then we went to circuit switching with ATM. That was technology for 3G, for UMTS. And then we went to Ethernet IP over packet. And with 5G, we embrace software-defined networking and the cloud. Every generation, we see that also actually with fixed networks. And I especially mentioned that because in the research center of formerly Alcatel, now Nokia, was also world-leading research on broadband over copper access. It started with analog telephony and then ISDN, and then ADSL, which was a big success for the Bell in Antwerp, with ADSL and then VDSL. So, and what you see is that the bandwidth is very similar of the mobile and the fixed technology, and that's not surprising because the underlying silicon technology that enabled the signal processing followed the same Moore's law. And every generation also has a defining application. In the beginning, it was all voice that drove the specifications, and 3G started with some specialized web services, and then 4G was really oriented to web and video streaming, and 5G is industrial IoT, industrial Internet of Things. But then every generation also has their unexpected applications, like SMS for the GSM, the true web on 3G, and the social media in the 4G generation. I pay you a beer if you can tell me what the unexpected application for 5G will be. For now, it's also crystal ball watching what 6G will bring for each of these categories. So that's still 30 years out, but we have already research in full swing, and a lot about new radio technologies that goes into even higher spectrum, terahertz, also an existing spectrum and lower spectrum, new technologies to make it higher capacity, lower energy. The compute platform is very much going to be AI ML. So AI ML that enable future applications, but also artificial intelligence and machine learning that define the way we will design networks. And then the defining application, our thesis is that we will see a fusion of the digital world with physical world and human worlds. So let me explain that a bit more. So what 5G has done is connecting humans and machines. The industrial IoT. What 6G will do is provide a much richer connectivity of sensors and synchronously capture the state of the physical world, state of our own human world with the digital world, capturing this, what is happening through massive scale deployment of sensing, but then also a use of AI to not only capture, but also understand what is happening. And so why is that important? So on one hand, we already talk a lot about metaverse these days, the digital worlds, in the context of extended realities. So you can then have a real-time model of yourself that is then teleported, if you want, to another location, and I can be in your environment as if I were there with you. That is the way that we think today of metaverse. We can also think of co-designing, working remotely on the same 3D and then print it out in a different location on a 3D printer. But it's more powerful than that. That continuous twinning of the digital world, of the physical world in the digital world, also allows you to then understand needs, predict possible outcomes, do simulations, analyze, and then plan for more productive outcomes back into the physical world or the biological world to actually enhance our daily life and our productivity. So these digital twins, they already exist in a precursor applications, for instance, in industrial automation. There are digital twins of machines that keep state of the machine, that allow to do predictive maintenance or repairs before failure happen. There's work on digital twins of cities, smart cities, and then, well, digital twins of ourselves, metaverse to some extent, but you can also think of your file at your GP doctor of being a first instance of your digital twin. Do that in future more in real time, and you see the healthcare possibilities there. So this is already happening today, but in 6G it will happen at a much larger scale with higher accuracy and in real time. And our thesis is that that will be a new killer app that will generate a lot of traffic load. You see here a very simple representation of the network. On the left-hand side, you see the access networks, wireless or fixed, that then goes over a backhaul network. We call it anyhaul, front haul or backhaul, to distributed edge cloud capabilities for network functions, for AI functions, for security functions, and then the IP optical transport network to interconnect these edge cloud with the central cloud. And what we are saying is this massive scale sensing will generate a lot of upstream capacity and traffic into this network. So a new killer app for bandwidth. And then not only the sensor information, but also the digital twin models. And think of them as 3D models with layers of information, parametric information, but possibly also abstract self-learned models, and that you continuously, these self-learned AI models continuously update each other through federated learning and transfer learning. So enormous demand for bandwidth. So these are the 6G era applications. Now let's talk about and I'll give you first an example of digital twinning of vertical farming. And this is a collaboration we have with a company called AeroFarms here in New Jersey, where AeroFarms is pursuing more efficient farming of produce salads, greenery, by repurposing warehouses. And the benefits is, on one hand, that you have your produce closer to the consumers. I mean, you're in an urban environment, so you have fresh produce. You repurpose the space, and you can do vertical stacking, so very efficient use of floor space. And then optimizing that also with lighting, shortening the growth time from 40 days to 12 days by continuous lighting, optimizing the water usage. It's a very clean environment. Going there, you have to be wearing clean room wear, so zero pesticides. And so we're collaborating with AeroFarms to create digital twins of that farms. And one problem is, how do you inspect all these shelves in an automated way, so that without the need for that scissor lift here that you have. You see here a person himself looking up. So yeah, the solution is to work with drones, and we have created our own setup in the Bell Labs in Murray Hill. On the left-hand side, you see the real-world view. On the right-hand side, you see the digital twin. And on the lower left, you see the camera view of a drone that is flying in between those shelves. And now succeed in starting that video. You will see that on one hand, that drone will start flying a predefined pattern. So we had to solve problems of wireless connectivity with low latency so that you can have real-time control of that robot. The controller of that robot is in a server, so to minimize the load on the drone itself. And then you see that drone doing localization. And I'll talk about localization in a minute, and then flying a predefined pattern. So that is one. But the whole purpose of that drone automatically flying around is doing in inspection of the shelves. And so it's capturing images of those shelves and in real time creating digital twins and analyzing the healthy growth of those leaves through video analytics, which is another area of research that we have at Bell Labs. So this is an example of how digital twinning enhances productivity and enhances the way we work and also the way we live. So to make such a future happen, we need a 6G network. It is going to be the essential network fabric. And rather, so we see 6 research directions. There's a pun intended. In the 6G era, there must be 6 research vectors. You see them summarized here. And rather than, because this is a very general audience, reading through all of them, I'll just give a few examples. So one example is the use of artificial intelligence and machine learning to communicate. So the problem that you're solving is you communicate over a wireless channel between A and B. And through decades of engineering, we've come up with a typical transmitter and a receiver model and you recognize the front end, the modulation, the error coding, and then the scheduling for the medium access control. And already today in 5G, we start implementing AI/ML on specific blocks to enhance the scheduling, to enhance the digital pre-distortion in the front end, as examples. We took a clean slate approach for 6G. What if we do away with all these layers of complexity and just let AI/ML figure out how to communicate between those endpoints? We've actually run the experiment, and depending on the channel, the endpoint just figured out its constellation modulation. The people that are in radio technology will recognize the QAM constellation, which is usually a regular grid. Well, in this case, depending on the channel condition, the AI/ML just figured out what the best constellation is. So decades of engineering and AI/ML figures that out in just a couple of hours. It's a very powerful tool. Is just one example how AI/ML will cause a paradigm shift in the 6G era. How we design networks, radio interfaces, how we will then standardize these radio interfaces, but possibly also how we orchestrate networks at large. It's just one example. And new radio technologies. So here are the bands that we already use today in 6G, in 5G, sorry. And so the low frequency band that typically have a large range of several kilometers. Then there's a lot of talk about mid-band in the 5G era in the United States. Some controversy about the C-band and how that impacts possibly the altimeters in airplanes. So we got a bit of news there. And then the high frequency spectrum for very high capacity, but at lower reach, so a few hundred meters. So 6G, we will see these same frequency bands repurposed with more efficient technologies, but we will also see new radio frequencies, the terahertz range with even higher capacity. Okay. We have demonstrated already in our labs that you can get multiple 10 gigabit per second over the air interface, fiber-like speeds. And then also we see other bands that are very attractive for the 6G, including very low frequencies, because these are interesting, not so much for the bandwidth, but for the coverage. But then it's not only about communication, it is also about enabling that ubiquitous radio and to use it as a sensor. And already today in 5G, we are using radio as a technology to get some understanding of what's happening in the physical world. Actually, cellular networks allow you to do some localization. You know in which cell you are, you know in which sector of the cell you are. If you do some time of arrival, you can get even to 10-meter accuracy where you are in the cell. Here in this experiment, we actually achieve 10 centimeter accuracy. And that is interesting with 5G technology. And you can see how in the map here, the 5G is tracking the location of the robot with 10 centimeter accuracy in this experimental factory. So this is 5G. And now in 6G, we want to go a step further, and we want to use the radio as a radar and use the back reflection. So we're using these high frequencies and wide bandwidths to get very accurate volumetric information. And not only volumetric information, but possibly also material properties. Are you reflecting off a metal surface? Are you reflecting off a mammal, a body that contains water? So, and combine these back reflections then with AI, and you get a good understanding with that ubiquitous radio of what's happening in the physical world. You can do things in a less intrusive way than cameras, visual cameras. So in places where you're not allowed to use cameras, and get still a sense of what's going on. So again, a bit playing with the words, a 6G network with a sixth sense. So continuing, then it's not only about the connectivity and sensing, but then also new network architectures, complete cloudification of network functions. And we see some of that already in 5G. Radio today, mobile networks are built in dedicated hardware boxes. And where we are going in future is, can we realize the digital signal processing that you require for radio on common off-the-shelf hardware that you have in future data centers? And so we've demonstrated that you can do that actually with GPUs. So the things that you have in your game boxes, the things that you actually have in every computer. These are actually massive parallel compute capabilities that you use for digital signal processing. And then once you have such an architecture capability, you have all the agility and flexibility that cloud applications, software cloud applications give you today. And so you can optimize the location using AI, using ML for more energy efficiencies, or for optimizing network performance if you are latency constrained, for instance. This is where we see the future of 6G going in terms of network architecture. And then I'll have a last challenge for 6G is the security. If you have all that data on your own digital twin in the network, you better trust what is happening. And the threat surface is really increasing. I mean, the number of devices that is connected is increasing. Multiply that with the number of subnetworks, the types of private clouds and public clouds, different networks, interfaces that you're transitioning, hardware components, software coming from different vendors, from open source. So you see an enormous threat surface, actually a zero trust infrastructure. And so how do you create a trusted service on a zero trust infrastructure? You can use AI/ML to, for instance, detect anomalies. You can insert anchors of trust so that you come to that trusted service. Very important area of research for 6G. So with that, I want to wrap up the more technical network part, the 6G. So the takeaway is we talk about the 6G era applications, where we see a fusion of digital worlds with physical worlds, thanks to a massive scale deployment of sensing and AI, and explained how that can improve our productivity and augment the way we work and live. And then we see 6 important research directions for the network technologies that we need by 2030. That is the technical part. And I don't know how you usually do this, but maybe I'll immediately continue with my non-technical part, and then we take a bit of discussion and questions. And I see Louis thumbs up, so that's the way to do it. So As you can also see from my background, I'm in the US, but we like the Japanese design. As Patrick said, I spent some time for my postdoc in Japan. That was because I did a PhD on liquid crystal displays. And in those days, the place to be, the pioneers were really in Japan. So that's where I spent my postdoc. And I wanted to reflect a bit on my observations, where I see Japan as a country that really cultivates the quality. I mean, we all know the quality metrics in the industry typically come from Japan, and that is, I think, because that's a culture that pays a lot of attention to detail, to the perfection. Think of a tea ceremony. You really focus on getting the perfect tea. People that do martial arts, you spend hours and days and years to get that movement perfectly right. Calligraphy is another one. So that sense of perfection is very much embedded in the culture, and it also comes through in how they implement their industry. On the other hand, in the US, what I see is a culture that is very much the Wild West, right? Go for rapid results. I was impressed when they took commitments. In 3 months, we need a prototype with this and this customer. I said, oh my God, this is never going to work. Yes, they pull this off. But don't do a quality audit. It will be full of red flags. So it's a very different approach. In Japan, I remember they take a long time to take a decision. They would debate for hours and hours. And as a European, I became a bit impatient. It's obvious. No. We need to really consider all the options. And part of that is also making sure that everybody is on board. And the other thing you should know about Japanese, they cannot say no. They cannot admit that they did not understand. So the way to go around that is to repeat again and again, just to make sure everybody understands. Because nodding is not saying I understood. Nodding in Japan only means I'm listening. So, but the contrast then is in the US, you have rapid decision. Oh yes, let's do it this way. But then in Japan, once the decision is taken, this is the decision, and there is a consistent execution towards a defined goal. I reflect, as a nation, they decided we need a high-speed bullet train. It was decided, and they all went for that. Shogun has spoken, the samurai follow. And the same was true for the flat panel displays. They were the first to have flat panel displays. I remember in Europe and in the US, we were going around with different options, liquid crystals, plasma, electroluminescent display. No, they decided LCDs, and they were the first. And nowadays they do it with robots as well. They are leaders in the robot. They decided, and that is the direction. Whereas in the US, there's very quick change of direction. Very agile. I use the analogy of the shogun speaks, samurai follow. It's a very hierarchy-aware society, actually. It's very important in a meeting who is sitting where, the order of speaking, whether you're facing the window or the door, all very important. And you achieve that hierarchy through the regular tenure, years of tenure in the company. In the US, it's your track record. You've proven that you can do it, bang, you're the guy. And the last point here on this slide is in Japan, there's a strong loyalty to the employer, but also vice versa. The employer is very loyal to and takes good care of its employees, as opposed to the US, where people are very mobile. Very easy to change company. I'm actually an exception, staying in one company for a long time, and also very mobile in the nation. It's very easy to move from one state to another. Even students, I mean, applying for student scholarship or so in California, when you live in New Jersey, it is part of the nation, and it is made easy also to move around. Cost of changing house is lower than, for instance, in Belgium, where you have that tax penalty that you and the how is it called, the notariskosten and all that makes moving a bit viscous, right? And we decide on a university more of pragmatic reasons. Yeah, it's a half an hour train ride from where I live. Or the opposite, your kids say, I want to go to Leuven because then I can go. In the US, it's very mobile and driven by also the ranking of the university. Okay, so this is a bit contrasting the industry. Then also the people are very much defined by their culture. And I have a bit of a thesis here that really goes through generations. Japan has been a country that was isolated for a very long time. They really protected any foreign contact because that would reduce the power of the shoguns. And for instance, Christian religion was forbidden because that questioned again the power of the shoguns. It was only late 19th century that they opened up the boundaries. And so that pretty much still defines today how many Japanese are dealing with foreigners. On the other hand, the US is a country of immigrants. Everyone is an immigrant, except for the American Indians. And so that gives this more, I would say, probably entrepreneurial mindset. Is you help even strangers because you depend on each other, and sometimes. So I also write here they're easy to communicate because as pioneers you depend on the stranger, so you easily make contact. I need your help. Do you know about that route and that route? Whereas in the Japanese, they're a lot more reserved. It's much harder to get contact, and they are, however, extremely polite and actually genuinely friendly. So I was warned before I went to Japan, it will be hard to make true friends. Well, that's not my experience. I have true friends in Japan that are still friends today that I visit when I go there. They warned me before I went to Japan, you will not be invited to private homes. Well, I have been invited to private homes. Colleagues took me fishing, and then we went to the home and prepared to fish. So I don't agree with that Japanese people are too close, then you cannot make friends. But they are reserved. Need to get a bit across that barrier, whereas the Americans are very easy to communicate, right? I mean, I remember walking in the supermarket and asked my wife, "Oh, what about this oil?" And somebody passed by, "Oh, I use that oil all the time." He was talking to us as if he knew us for years, and then he went on. So, and for us Belgians, we sometimes misunderstand it as superficial. I would not say that is superficial. That is, at that moment in time, a genuine interest to help you. And again, that goes back to this pioneer culture. You're dependent on strangers. And I think also new immigrants, when you move somewhere, you have to build up your social network. So you have to become more open. And that lives. Going back to Japan, a culture of modesty. You don't stand out. Everybody's uniformly dressed. Oh, don't change the color of your jacket. Even the professor or they all dress the same way. They all come by public transportation. You don't stand out. On the contrary, the US is a nation of self-confidence. I put it here. We Belgians sometimes tend to think they're a bit arrogant, but it's again. Probably self-confidence out of a need of pioneers. In the Wild West, you arrive in a town, you enter the saloon and you say, "Hey, I'm a carpenter. I can do a good job. Do you need me? You have to advertise yourself. And that's probably where that is coming from. US is also a very award-driven culture, awarding excellence. You probably have seen it on the Zoom calls that we have these days. Americans would very often have all their awards behind them. Yeah, so I already mentioned the very polite and the adherence to social rules in Japan, more formal dress, the seating order in a meeting. So the highest in faces the door, for instance, it's at the head of the table. The US is more relaxed, right? If the boss of the company comes in blue jeans, you use the given name. It's a lot more informal, making conversation easy. It helps to oil the collaboration. And then the last thing here is, the Japanese cherish the small things. You have been in Japan, these little boxes where you can put in all kinds of things, very detailed craft work. Yeah, they're confined in small spaces. So architecture is also reusing space in very efficient ways. And that eye for detail probably led them also to such technologies as the early cameras and perfection in technology. Then by contrast, US, everything is bigger in America. Right? And I was last week in Texas, and everything is even bigger in Texas. The vast space and size of the buildings, and again, another contrast. But then, and I'll finish up with that reflection, as every expat will experience, in the end, they're all humans. And that's how I always approach wherever I am. Humans with good intentions, engineers with a healthy curiosity and an ambition to achieve a good outcome. And if you approach people in that way, you will find friends wherever you go, whatever the cultural differences are. And with that, I'd like to finish here and open it up for questions or reflections from your side if you have similar experiences.
All right, thank you very much, Peter. That was a very nice, insightful talk with some eye-opening insights there. Good note to end on as well. So thank you very